Um, we often think of Poincare as some kind of opponent of Hilbert, but in fact, Poincare recommended Hilbert for the Lobachevsky Prize. It's a very big prize. Poincare and Hilbert knew that they were the two most important at the time. And Poincare wrote, in 1899, on the occasion of a Gauss-Weber Jubilee, there was a 50th anniversary of these two famous mathematicians, well, Gauss very famous, Weber, and they had a celebration. And Hilbert published a memoir called Foundations of Geometry. Poincare says it is filled with the most original ideas. Poincare liked this. Through the 1890s, Hilbert frequently lectured on the foundations of geometry. He published many articles about it. Poincare studied all of this very carefully and wrote a very long review of the foundations of geometry. So he published several reviews of that book, actually. He praises Hilbert's thoroughness and precision in stating his axioms. Hilbert gives axioms for Euclidean geometry. Poincare says, okay, these are the most accurate axioms anybody has stated. They're very precise, they're very clear. He especially praises Hilbert's vast array of independence proofs. Hilbert says, okay, we need the parallel postulate. One of the axioms is the parallel postulate. He says, we couldn't do without that because if we didn't have it, there would be other geometries where it's false. And he shows this for many axioms. For each group of his axioms, he says, we need these because if we didn't have them, there would be other geometries where they're false. Of course, the most famous was the parallel postulate. This was the most famous example. Hilbert shows that if Euclidean geometry is consistent itself, then so are two non-Euclidean geometries. That if Euclidean geometry is consistent, these other two have to also be. Well, the first, of course, is just Euclid's geometry. You've got to have a line L, a point on that line. There's exactly one line through that point that doesn't meet the first line, exactly one parallel. Lobachevsky's geometry, which we now call hyperbolic geometry, you have a line and a point B that's not on L. There are many lines through P that don't meet L. Now, they're all within a range. They're just slightly differently angled to each other, but they don't meet that other line. And Riemann's, which we today call elliptic geometry, where every two lines in the plane meet. Every two lines meet. You can't have one line up. These were well known. But Poincare faults mathematicians who thinks those are all the geometries. Poincare says, those mathematicians, they imagine what they call general geometry, including the three systems that Euclid, Lobachevsky, and Riemann, and they think, they call it general because they think no other geometry is conceivable. That's it. And Hilbert will show them that they're wrong. They will lose this illusion if they read Hilbert's book. They will see these frameworks in which they wanted to enclose us burst open on all sides. Hilbert finds many other kinds of non-standard geometries that all violate some axiom of Euclid. Well, they all violate one of Hilbert's axioms for Euclid. Euclid's axioms weren't that thorough, but Hilbert's are. They all violate, but only violate that. There's lots of them. He gave several other non-standard geometries, which I won't describe unless we want to talk about them. But Poincare also praises Hilbert for giving such precise axioms that a machine could use them. Don't have to know what you're doing. Not just abstract, they're mechanical. Monsieur Hilbert, I like to think of Poincare. I'm not going to read it in French, but I like Monsieur. It's just good. It's a good. Monsieur Hilbert sought, so to speak, to put the geometry axioms in a form where they could be applied by someone who did not understand the meaning, since he had never seen either point or a line or a plane. Poincare is that's meant to be a joke. Of course, everybody's seen points, lines, and planes. But he's making the point that it doesn't matter to the axioms. You don't use those meanings. According to Hilbert, the reasoning must reduce to purely mechanical rules. Poincare saw two demands where Hilbert only made one. Hilbert indeed said that the proofs have to still work independently of what the terms mean. Don't have to use the meaning point line of plane, you just use the axioms. You should be, instead of point line plane, one must always be able to say table, chair, beer stein. Sometimes you'll hear people try to explain why he chose those three nonsense words, but when you read the other things he wrote, there is no reason. He just meant that he did nonsense. He gives much more nonsensical. There is no explanation why he chose those three, just nonsense. But Hilbert did not pay attention to the logic. He offered no formal logic, let alone did he say that logic should reduce to mechanical rules. He simply did not say anything like that. He had not thought anything like that yet. That's Poincare's own contribution. Poincare jokes about it. Poincare is a funny guy. He likes jokes. In Hilbert's Foundations of Geometry, to prove a theorem, it is not necessary or even useful to know what it means. Okay, did you ever, when you were in school, try to give a proof without knowing what it meant? It's, it's a joke, but one could replace geometers by the logical piano imagined by Stanley Jevons. That was a machine that Jevons actually built. We'll see a picture of it. Or if one prefers, one could imagine a machine where one puts axioms in one end while collecting theorems at the other, like the legendary machine in Chicago where pigs go in one end alive and come out turned into hams and sausages. There was no such machine. To this day, there is no machine that you put a pig into it and it comes out butchered. There are machines that you use in butchering pigs, but they don't run themselves. Mathematicians have no more need to know what they are doing than those machines. Now, Poincare very definitely believed that using formalized geometry the wrong way would be a terrible mistake. He says there is no need to say how deadly this would be for teaching. Please do not take high school students and try to teach them geometry by showing them a machine that will crank out the theorems. Do not teach them geometry without telling them what point line plane means. This is not the way to teach geometry. And he says it would also be deadly for research in geometry. Researchers would give up having ideas if they thought this machine was just going to spit out all the theorems. It'd be really bad for those purposes. What was formalizing was good for exactly one use. He says, I do not hold the formal character of geometry against Hilbert. He had to arrive at that, given the problem he set himself. Hilbert had to have a purely formal geometry because Hilbert wanted to cut the number of fundamental axioms of geometry to a minimum and list them completely. He wanted to say everything you need as briefly as possible. But in reasoning where our minds are active, where intuition still plays a role, in live reasoning, so to speak, believe me, Poincare is in favor of live reasoning. Go have your minds be active, but not for this problem. Because when your mind is active, it's hard to avoid introducing some axiom or postulate which goes unnoticed. You will slip in false assumptions. Poincare does this all the time in his own work. His own work is full of unstated assumptions and even mistaken unstated assumptions. And he's not unhappy about that. This is what live thought is like for him. But that's not what we're doing here. It's only after reducing all geometric reasoning to a purely mechanical form could Hilbert be sure he had succeeded in his plan, that he had actually stated everything being used. The way you know you've stated everything is that the machine can use your axioms and get all the theorems. Now, this time they do not have very good ideas about logic. They do not have our modern idea of a complete theory. When Hilbert talks about complete axioms, he just means they imply all the theorems he thinks they should. He has no technical meaning for that yet. This is 1902. Nobody has a technical meaning for it. But Hilbert showed that his axioms actually said everything we need to say to define Euclidean geometry. Nothing hidden there, because the machine won't respond to anything. A machine could do this. Poincare considered this a great goal, not the only goal. This is not the way to teach students. This is not the way to conduct research, but it is the way to make sure your axioms are perfect. And he was serious about the machines, not joking about the pig killing machine, not joking about machines. Charles, that's Poincare in 1902. Charles Babbage had imagined a computer around 1840. This idea was not there. And we know how he did. This is a picture of the control for what's called a Jacquard loom. One Jacquard in 1803 had already found a way to make punch cards control a weaving device to weave very intricate fabrics. This put tens of thousands of weavers out of work. It was a great success for the bosses. It decimated the profession. And he used punch cards. He said, how do I tell the machine what I want it to weave? Oh, I'll take cards and I'll punch holes in them, and that will be the instructions. And Babbage looked at that and said, oh, I want to tell a machine how to do math. I'll use that. That's actually where Babbage got the idea. Babbage was aware that in France, many long calculations for like maps and calendars were being done. You would have a room full of people who really didn't know much math. They could just add and multiply, but you would give each one explicit instructions. You would say, the person in front of you will hand you a slip of paper with two numbers on it. I want you to do this with those two numbers, write this part down, write that part down, and hand that to the person behind you, so that no one in the room knew what they were calculating. They just knew their step, and it worked. And Babbage says, okay, if we can do it with people, we can do it with machines. The whole point of these people was they don't know any math. Right? They didn't have enough people. They had people who do that job. So he built an analytical engine. People will tell you he built it, but if you read more closely, he didn't ever build it. This is just a part of it. Built. It never was built. It never worked. It was designed, and part of it was built. Never built the whole machine. He never pretended he built the whole machine. He was very frustrated that he couldn't get enough funding from the government to build the whole machine. Ada Lovelace, mathematician, the daughter of the poet Byron. Byron is a very famous, very dramatic poet. Ada's mother did not want her to be like her father. Please be not so dramatic. That's not, it's bad enough for him. It's worse for you. Don't. So what she did was she said, I got my daughter. I do not want her to become a crazed poet. I'll teach her math. She'll be good at math. And she was good at math. And she got involved in Babbage's project, and she really liked the idea of this machine. And she wrote a very nice set of instructions to calculate some integrals that you or I or anyone could do if we had enough time following her instructions, but the machine could do it quicker and faster, and except that the machine never existed. But the set of instructions existed, and sometimes people say that was the first computer program because it was formatted for this. It wasn't just rough instructions, it was instructions that this machine could read, except that the machine didn't exist. And then in 1870, Stanley Jevons imagined and built a computer that would do logic. He took the idea of the analytical engine, he took the idea of Boole's logic, and he built that thing over there. That did get built, and it did work. It would calculate truth tables with four columns. Well, four variables. So there's what, 16 rows. Now Jevons knew very well that was too small to do anything practical. You could not, because anything that thing could do, you could do by hand pretty quickly. But the point was he actually built it so that you could not understand, you could build a bigger one, and then that would be able to do real stuff. So when Poincare says you could put the axioms into Jevons's piano, he doesn't mean that thing there. He means the one Jevons imagined that hadn't been built yet, the bigger version of that. But the small version, unlike Babbage's, did actually get built. This is a brief history, but it's okay for us because Poincare was not concerned with details. Poincare could take this kind of rough sketch and see, I see where this is going. Babbage sees where it's going, Jevons sees where it's going, Lovelace sees where it's going, and I see where it's going to. This is going to work. There will be machines that can actually do very hard calculations, that can actually do hard logic. These machines will exist someday. I mentioned last time, Poincare his family supported the Second French Republic before there was a Second French Republic. They supported the Republic under the Empire. And their view of the Republic, this will be progressive, this will be liberal, this will be scientific, and we can do everything. We can cure all diseases. We can make all cities clean and safe. We can lay cables across the Atlantic Ocean. We can do all of that. Poincare believes this because his parents raised him to believe it. Everyone he knew believed it. So this is enough for him. He says, okay, it doesn't work yet, but it'll work. One would be able to confide Hilbert's axioms for geometry to a reasoning machine, for example, Stanley Jevons's logic piano, and one would see all of geometry come out. Now, again, he does not have the modern logician sense of what he means by all of geometry. He just means all the theorems it should be. Whatever it should be, they'll all happen. He doesn't have the idea of a complete theory yet. Nice guy. He was a very friendly person, but he was a little reserved. You had to know him before he would talk to you much. Now, he knew this was too small, so did Jevons. And he was serious about the future, as was Jevons. They both, this is a proof of concept, and this will work. Hilbert was not thinking that way when he wrote. Poincare said Hilbert reduced his logic to mechanical rules. Hilbert did not reduce his logic to mechanical rules until after Poincare published this. I mean, picture yourself, you're David Hilbert. You believe you are the best mathematician in the world. You know you are the second most famous mathematician in the world. You read, when the most famous writes about you, you're going to read it. So he knew what Poincare was writing, and he saw that Hilbert was right about the mechanical thing. He saw that was actually true. Now, Hilbert didn't care about actual machines. So far as I know, Hilbert never said anything about actually building machines. Do this, although, as we know, actual machines got built by people influenced by Hilbert, namely Turing and von Neumann. That they actually meant build these machines, and the machines got built. Hilbert did care that formal mechanical reasoning is just manipulation of finite strings of symbols without understanding them. How did people used to say in those days, for correct logic, you can only use finitely many words to define a concept. Well, obviously, you can only give finitely many instructions into a machine. No question. Of course, that's going to be finite. And he cared about that aspect of mechanical reasoning, which a lot of people at the time called mechanical. Often they would say mechanical to mean routine, cut and dried. They didn't actually necessarily mean a machine, but they believed anything that could be made that routine, that cut and dried, if you know the expression, could be done by a machine. To say set theory is true, we need to understand infinity. Set theory deals with infinite sets, and it deals with the set of integers, which is infinite, the set of reals, which is bigger and infinite, and then the set of sets of reals, which is bigger. And a lot of mathematicians at the time said, this is crazy. We can't know infinite things. Stop talking about the set of all integers. It's infinite. And certainly don't talk about the set of all sets of integers. That's just crazy. And Hilbert says, okay, you're right that if we're going to say these things are all true, we're claiming to know the infinite. But if we just want to show that set theory is consistent, that's just a question about finite strings of symbols. Consistency of set theory is not about the infinite, it's just about finite strings of symbols. All we need to know is that the formal symbol rules of set theory will never lead to 0 equals 1. Because of course, by standard logic, if they lead to any contradiction, well, any contradiction implies everything. They'll imply 0 equals 1. And since they clearly implied that 0 doesn't equal 1, if they also implied 0 does equal 1, they would imply a contradiction. So we don't have, if it implies any contradiction, it will imply 0 equals 1, and vice versa. So all we have to know is that those rules will never lead to 0 equals 1. In fact, Hilbert did believe that Cantor's theory of infinite sets was true. He absolutely believed it was true. He didn't doubt it at all. He liked it a very great deal. But he argued that if say, Kronecker doesn't like it, Kronecker says, I can't believe Professor Hilbert's proofs because he uses infinite set theory. And Hilbert says, oh, you can still believe my proofs because my proofs don't depend on that set theory being true. They only depend on it being consistent. As long as that set theory is consistent, it won't imply any false statements about finite numbers. Because we already know that it implies all the true statements. He can prove that set theory implies all truths about finite numbers. So if it's consistent, it can't imply anything false about finite numbers. So even if all you care about is finite numbers, you can still use the transfinite set theory, because anything you get that way will have to be true. Whether you believe your intermediate steps or not, the conclusion you draw about finite numbers will have to be true, or about finite geometric shapes. And you can read the book where Hilbert does this. He has a book, it's translated into English as Intuitive Geometry. And for example, in this book, he proves if you take a sphere, a perfect sphere, you can't bend it at all without putting a kink in it. There's no way to bend a sphere without denting it sharply at some point. And to prove this, he says, look at this consideration, intuitive geometric consideration, look at this. And at this point, we would use analysis to show, because at some point that proof has to use advanced calculus. And he says, okay, that uses infinite sets. That part of it uses infinite sets, but then it gives you an intuitively meaningful conclusion at the end. And because you know the theory that set theory is consistent, you know that conclusion has to be true, even if you don't believe the exact analytic steps, because they involve infinite sets. So you can actually read, he's got this book where he actually says, here's the intuitively meaningful part. Here's where you would use infinite reasoning. Here's the intuitively meaningful conclusion. We just need to prove by finite means that the symbol rules of set theory will not lead to 0 equals 1. It's not good enough to hope they don't. We have to know they don't. And if we're trying to do everything finitarily, this proof has to be by finite means. We can't use the infinite for this part of the proof. We have to show by finite means that the symbol rules will never lead to 0 equals 1. This is Hilbert's program. The point of the program is to say, even if you only believe statements about finite numbers, you can trust reasoning that uses set theory because it only implies true statements about finite numbers. And but the consistency question, that's just about finite strings of symbols. Because a proof is a finite string of formulas. A formula is a finite sequence of symbols. You just need to show that your rules will never, these rules will never be able to produce 0 equals 1. He didn't know how to do it. And in fact, he proposes, let's do it for arithmetic first. He wants to do it finally for set theory, but that's obviously going to be harder than arithmetic. So let's do it for arithmetic first. Let's show by finite means that arithmetic is consistent. We should be able to do this. And Gödel's very great incompleteness theorems showed this was a very great mistake. This was not a common mistake. This last step, that because it's about finite strings of symbols, we should be able to do it. That was a big mistake, but a great mistake, because it took a great theorem to show that it was. Hilbert in 1900 says, in investigating the foundations of science, we must set up a system of axioms. Hilbert believes this already. Mathematics, any science finally has to have axioms. That's why mathematics is the best science, because mathematics normally does have axioms. but they all need axioms. But above all, I wish to designate the following as the most important among the numerous questions which can be asked with regard to the axioms to prove that they are not contradictory. You don't want contradictory axioms, especially because you know that any contradiction implies everything. You can prove anything you want from contradictory axioms, except you don't care because you can't believe the axioms because they're contradictory. So we need to be able to prove the axioms are not contradictory. To put it in terms that are not his, we need assumptions weaker than Peano arithmetic that will suffice to prove set theory is consistent, and that should be possible because set theory is just a bunch of finite simple strings. It's not really. We know that it's also true, but we don't need that here. We're just showing consistency. That's just a question about finite strings of symbols. Even though Hilbert absolutely believes the whole theory is actually true. We do know infinite sets, he believes. But he also talks to mathematicians who want to say, well, I don't trust you about infinite sets. He says, you don't need to. You only need to trust me that they're consistent. Well, and don't trust me in the long run. We should prove they're consistent from principles that finitists already accept, something weaker than Peano arithmetic. And this was wrong. It was a truly great mistake. Gödel shows that even all of Peano arithmetic will not prove that Peano arithmetic is consistent, let alone some truly finite part of it. Let alone will Peano arithmetic prove that set theory is consistent, it won't even prove itself as consistent. Not only will no finite part of it prove it's consistent, even the whole of it won't prove it's consistent. So Gödel buries the technical aspect of the Hilbert program. He doesn't just show it can't be done, he shows it is infinitely far from feasible in two different directions. So could arithmetic possibly be inconsistent? So this is how a lot of mathematicians at the time respond. They say, Professor Hilbert, you're trying to prove arithmetic is consistent? Well, my grandfather's been using arithmetic since he was a kid, and there's never been a problem. And Professor Hilbert says, okay, I'm not talking about the arithmetic your grandfather uses. I'm talking about formalized arithmetic, and eventually formalized set theory. That's what we really want to do this for. We want to do this for formalized arithmetic, where you have the axiom scheme of induction. Let phi of x be any formula in the language. We have an axiom that says if 0 has phi, and for every x, if it has phi, its successor has phi, then every x has phi. Okay, the notation is, yeah. We pose this as a separate axiom for every formula in the language. You might wonder, would it be enough to do it just for some formulas? And actually, yes, of course, you don't need to do it for all of them. Some are redundant, but you do need infinitely many. You cannot get by with less than infinitely many cases of the induction axiom. Some are simply redundant, right? I mean, phi of x might be x is equal to 0 or not equal to 0. You didn't need that. But you do need infinitely many formulas to make this work. It's kind of a bold claim to say that you grasp the expressive power of general formulas phi x in the language of arithmetic. I mean, how long is the average formula of arithmetic? That's a joke question because they get infinitely long. There is no average length. They get infinitely long. No human being has ever imagined a formula of arithmetic that had more than 1 trillion letters in it. Not in any concrete terms. And yet we claim to know this for all formulas of arithmetic. So that's a kind of a bold claim. I think we do claim it. I mean, really, we think we know what we're doing here. We say, yeah, we know what formulas of arithmetic are. We do know this, in fact. But the question isn't whether what we think we're talking about is consistent, because, yeah, obviously, practical arithmetic is consistent. People have been using it for millennia. Doesn't lead to any problems. Sometimes people argue about whether they got the right change, but it's not really about it. We do claim it. But here's the point I owe to John Mayberry. I think this is a very good point. We've only ever applied induction for conditions phi that make sense. Nobody has ever taken some random string of some random well-formed formula that they can't read and ask themselves whether induction looks true for it. Because you can't read it. Nobody does that. We don't do induction on formulas we can't read. Obviously, most formulas of pound arithmetic we can't read because they're too long and they're too complicated. And we've never done those. The inductions we've ever actually done were all ones that made sense. And if the formalism is concealing an inconsistency, if there's something we have some inconsistency we haven't noticed, we should expect it to lie in the conditions that do not apparently make sense, because the ones that make sense are the ones we'll be right about. If we're wrong, it'll be about something we don't understand. Well, okay, if the only mistakes we can make are ones we can't understand, we shouldn't be surprised if we don't think of them. So it's not trivial. So this is a bold claim to say that you really know this for all formulas, including ones that nobody could ever possibly understand. And yet it's a claim we make. And John Maybury believed absolutely, yes, absolutely believes it's consistent. But he wants to say that's not a trivial statement. There really is. We're really going beyond what we could ever check concretely. Gödel, 1931, proves that no plausibly comprehensive axioms for mathematics will suffice to prove their own consistency. Right? This is, Hilbert had asked for something much more. He wanted plausibly comprehensive axioms for mathematics that some finitary processes will prove consistency. Gödel shows no, even the whole comprehensive foundation won't prove its own consistency, let alone some finite parts should prove its consistency. The day we focus this on Pound arithmetic, at least when I teach Gödel's theorem, I prove it for Pound arithmetic, and this is the right way. That's why I do it. It's the right way to do it. But precisely Gödel's argument shows there is no single place to put consistency proofs. There isn't one foundation for all consistency proofs because it won't include its own consistency proof. And so there's none for proof in general. There is no one foundation for all mathematical proofs. By one, I mean one recursive first order axiom set. That's the actual theorem. You can prove it. And I think it's the correct theorem. I think that's the correct understanding of it. I think any foundation for arithmetic that we can actually understand will be recursive. Oh, and the first order wasn't required. You really do this. You have a recursive proof relation. You have Gödel's theorem. And a recursive proof relation and can interpret arithmetic into any foundation. Now, set theory, of course, any reasonable set theory will prove PA is consistent. Second order Pound arithmetic proves that first order is consistent. Sure, you take a stronger theory, you can prove the weaker theory was consistent. That's nice. It helps us believe that we're on the right track, that what we're saying makes sense. So does Pound arithmetic plus the axiom that says you can state in Pound arithmetic that Pound arithmetic is consistent. That theory implies that Pound arithmetic is consistent. Now, if Pound arithmetic isn't consistent, of course, it already implied Pound arithmetic is consistent. So this doesn't encourage you in any way, but it is say, sure, PA plus the axiom saying it's consistent proves that PA is consistent, but it now doesn't prove that the stronger theory is consistent. And when you look at the proof of Gödel's theorem, the way I prove it in my class, we do it for Pound arithmetic, but it only takes about 15 minutes discussion to see that it will continue for any consistent recursive extension. It should be true in some recursive small fragment. Well, it's important to talk which fragment. So I entirely believe this empirical claim from Georg Kreisel. Georg Kreisel was a very skilled logician. He was sometimes hard to get along with, but he was a really good logician. And he says, we cannot prove consistency of Pound arithmetic from any assumptions that are more plausible in the first place than consistency of Pound arithmetic. The real reason you should believe PA is consistent is that if you get used to working with it, you can tell it's consistent. There are many technical proofs of consistency of PA from other assumptions, but those assumptions are, well, set theory is simply a stronger assumption. There are other proofs to use incomparable assumptions, but no proof of consistency of PA is more plausible than just understanding PA and seeing it. I can tell it's consistent. They're important for technical reasons, absolutely important to know what other assumption can prove consistency of PA, but they are not the reason you should believe PA is consistent, because they're no more plausible than the consistency itself is. The same will work for any foundation. Gödel's theorem it's a fantastically stable theorem. You can't just duck out of it in some way. You can duck out of it in implausible ways, but not in reasonable. Any theory T that could be a logical foundation for mathematics has to include at least arithmetic. It can't be a foundation for math if it doesn't give you arithmetic. And Gödel proves in that case, arithmetic is not going to prove T is consistent. Indeed, all of T is not going to prove that T is consistent. Now, there's a lot more to know about this, and the fuller story includes a lot of things that Hilbert thought about after he talked with Brouwer on the beach in 1909, and followed him in correspondence and kicked him off the editorial board of that and all this. Lots more to say about completeness. The logicist philosophy was more or less destroyed by this result. Remember, the logicians for Klein were people who gave precise definitions. That became universal. By 1930, all professional mathematicians, essentially all, gave precise definitions. Great. So then we came up with logicism, was this philosophy that said mathematics can be reduced to pure logic. And Gödel's theorem said, no, it's just not going to happen. Now, there were people who kept saying, I can find a way to make it happen. There are people still trying to say they can't find a way. No, even they admit, yeah, it looked bad for us. And in fact, it was decisive. David Hilbert, 1932, draws the conclusion. The question of what it takes to give proofs at all becomes the question of what it takes to prove a given result. You cannot give one foundation that proves all of mathematics. It won't even prove its own consistency. A given foundation can prove lots of things, but you might need a stronger foundation to prove other things, like, for example, consistency of that foundation. The question of what it, so there is no longer one notion of proof in mathematics. There's proof from these axioms, from those axioms. There is no final axiom step. You can say, well, that's the one I meant. This idea propelled the decisive early 20th century work on logic. So it's Gödel's answer to it that made this explode. But it was Hilbert's idea that provoked Gödel's answer. Hilbert's idea became the propeller for lots of work in logic. It was a truly great idea, and another genius showed it was a mistake. We sometimes say truth comes more readily from a clear mistake than from a confused truth. You know, if you make a clear mistake, you can correct it. You can spot that it's a mistake. If you start with true ideas, but they're confused, you don't know where to go with that. You might not. Gödel's incompleteness theorem created modern logic as a mathematical research field. I was talking to somebody in a YouTube interview. He said, well, what are some ways that Gödel's theorem is overrated? I said, there are no ways it's overrated. You can misunderstand it. There are people who misunderstand, but you can't overrate it. It's just here. That's why modern logic. Well, I mean, if it had been false, who knows what would happen if it had been false? But historically, that's what modern logic comes from. Now, you can have a working foundation that will avoid the incompleteness phenomenon. By a working foundation, I mean a foundation suitable for some part of math. It will not be a foundation for all of math. Gödel incompleteness is not separable from any whole foundation for math. But you can have a working foundation for a subject that avoids the incompleteness there. Alfred Tarski showed that elementary algebra and elementary geometry are complete. He gives precise definitions of what he means by elementary algebra, what he means by elementary. And he shows these are complete theories. The incompleteness phenomenon does not apply to them. And this is a very lively research in model theory around the theme of O-minimality and related kinds of restrictions. It's an exciting field. A lot of stuff goes on. Tarski's precise versions of elementary algebra and elementary geometry cannot define the integers. That's important. If you could define the integers, you could reproduce Gödel's argument. So in this, we can talk about 1 and 2 and 3 and 4, but we cannot say for every whole number in elementary algebra, elementary geometry. You cannot define the notion of all whole numbers. You can say all real numbers, but you cannot define, and you can list the whole numbers, 1, -1, 2, -2, 3, -2. You cannot say that they are all, because if you could say that, then you would get Gödel's incompleteness. They include every concrete truth of arithmetic. These theories prove that 217 times 4091 equals whatever it equals. But whatever it equals, these axioms will prove it equals that. But these axioms, these axioms will prove the commutative law because they assume the commutative law. But they will not, there are lots of theorems of arithmetic. They will not prove that every positive number is a sum of 4 squares. A square whole sum of every positive integer is a sum of 4 integer squares. They will not prove that. They will prove every concrete truth of arithmetic, but not a lot of technicals. Now, lots of genuine problems, as in algebraic number theory or geometry, can be put into these contexts. There have been at least one famous conjecture in algebraic number theory that Hrushevsky proved by showing you could express it in Tarski's elementary algebra, and then using the general features of elementary algebra to show that it had to be true. This is working math. This does real serious stuff. Because you work in contexts that themselves do not support, I say, the fearsome complexity. I like fearsome complexity of mathematical induction. Mathematical induction is hugely complex. And if you don't have that, okay, but lots of problems. In fact, no problem needs all of it. It's a theorem. You can show that any theorem provable in Poincare arithmetic is provable in some strictly weaker fragment. If you can prove a theorem in Poincare arithmetic, that proof only needs finding many axioms. And Poincare arithmetic does prove the consistency of every finite list of its axioms. It just can't prove consistency of all its axioms. So yeah, no theorem of Poincare arithmetic uses the whole complexity of Poincare. But Poincare arithmetic as a subject does use it all. But there are contexts in algebraic number theory where you can actually say, I only need this much of it. I don't need the whole complexity. And so I can do this in a context that avoids incompleteness. Precisely. This does not let you stop thinking about Gödel incompleteness. This tells you keep thinking about Gödel incompleteness. Whatever you do, make sure that your assumptions don't invoke it. They don't say, oh, just ignore incompleteness. They say you have to make sure. For example, the things you have to not do. Don't include the trig function, sine or cosine. You can't have a function theory that includes polynomials plus a sine function if you want to avoid the incompleteness phenomenon. Because sine pi times x equals 0 would define the integers x. Those will be the whole numbers x that meet that equation. And once you can define the whole numbers, you can give the incompleteness proof. So you have to not use the sine function in these contexts if you want to avoid incompleteness. which is to say that the subjects as a whole, they don't tell you to stop worrying about incompleteness. They tell you to worry carefully about incompleteness. Make sure you don't get any of it if you're trying to do this kind of approach, which can be a very helpful approach, in fact. Gödel also showed the first important case of concrete incompleteness of set theory. That is, it's an incompleteness result. Something is neither provable nor refutable from the axioms, but it's something of mathematical interest. Specific statement of set theory that was already interesting, but doesn't follow from, well, some given version of the axioms. Because remember now, we've all learned there's no such thing as talking about a proof. You have to say proof from certain axioms. The axiom of choice. The axiom of choice does not, if you take the Zermelo-Fraenkel axioms, except for choice, leave that one out, they will not imply the axiom of choice. They won't prove it's true. They won't prove it's false. Happily, they won't prove it's false. So that means it's consistent to add it, which would do, but they also won't prove it's true. This is a concrete question. People worried about this for a long time. When Zermelo gave his axioms for set theory, he used it as a context for discussing the axiom of choice and the theorem that the real numbers can be well ordered. You know what a well ordering is. You know, can the real numbers be well ordered? Well, it's absolutely standard set theory today to say yes. You can put a well ordering on the reals. However, you cannot define that well ordering. There is no definable well ordering of the reals in Zermelo-Fraenkel set theory. It's not definable. You can prove it exists, but you can't define one. And to a lot of mathematicians at the time, they said, that doesn't even sound right. How can you take the continuum apart and do it one after another? No, you can't order the continuum one after another. That just made no sense to them. Okay, well, Zermelo proves you can with the axiom of choice, but you still can't define such a way. And Gödel showed, I believe, both of those. I'm not sure he proved the undefinability, but he certainly proved the independence. You can define a well ordering with ordinal parameters if you assume V equals L, because everything is definable with ordinal parameters, but not without. The continuum hypothesis. Remember Cantor, he says, okay, I'm going to deal with infinite sets. I know this has driven people crazy in the past. I know Galileo set out to do it, and he said, this is just too weird. I'm not going to keep doing this. And Bolzano set out to do it. He said, it's just too weird. I'm not going to let the weirdness stop me. I'm just going to go ahead and do it. I'm going to say two sets of the same size if you could put them in bijection with each other. And so there are just as many rationals as there are whole numbers. Well, they're ordered very differently on the line, but you can write all the rational numbers in a sequence like all the whole numbers. You can do that, all the algebraic. And then he says, okay, so are all infinite sets the same size? Can every infinite set be written as one sequence like the natural numbers? And after a whole lot of work, this is a very difficult proof to discover, even though it's an easy proof to give nowadays in courses. He shows, no, the real numbers cannot be listed like the natural numbers. No, you can't list all the real numbers in one list the way you do the natural numbers. And then the next thing he says, okay, are the reals the smallest set that you can't list, or is there something in between? To this day, there's no generally accepted answer to that question among set theorists. Truth is, pretty much everybody likes, no, there aren't any reals. But they feel they can't prove it. They don't want to take it as an axiom. The continuum hypothesis. The second serious question Cantor asked about transfinite sets is not currently answerable in statement sets. And Gödel showed that it was consistent. Colin in 1963 shows that its falsity is also consistent. So it's not provable. The fact that these kinds of concrete incompleteness, interesting incompleteness, not rigged by a logician, is another witness that, as Hilbert said, mathematics can never be grounded solely on logic. Consequently, Frege's and Dedekin's attempts to do so were doomed to failure. You're going to have to, if you want to believe things about transfinite sets, you're not going to get them by definition. You're going to have to say there's some stuff you believe. You're going to have to start with contentual axioms, serious axioms about transfinite sets, or you won't get any serious results. You can't get them from pure logic. You have to get them from substantial assumptions. Not surprising, but now there are two responses to Gödel incompleteness. One is, oh, that means foundations is ugly. I'm not going to do foundations. No, don't say that. I mean, if you don't want to study incompleteness, that's okay. But it's not ugly. It's beautiful, actually. And don't give up on foundations. The other is, okay, from now on, we'll have to do what Hilbert said. When we talk about a proof, we'll have to say proof from what axioms, because it matters. There is no final set of axioms that will cover everything. And different axioms will cover seriously different theorems. So keep track of what foundations work for what theorem. Now, this is what Harvey Friedman says. He can imagine a time when you won't be able to publish a paper in a math journal without a reversal showing which axioms in his hierarchy your axioms are equivalent to. I think Harvey's wrong about that, but who knows? I could be wrong. Between me and Harvey Friedman, if we say different things about logic, you want to listen to the Harvey one. I don't mean every mathematician should spend all their time asking what axioms they're using, although to be fair, it's commonly quite clear. It's commonly not a difficult question. So does anybody worry about the foundations of this building? Well, of course, yeah, lots of people do. Lots of people do, but they're engineers, they're not us. And we can use this building because lots of people worry about its foundation. So you and I don't worry about the foundations, usually. As I said last time, go read Sophus Lee, read Felix Klein, read Paul Gordon. There is a difference here. I earnestly urge you to read Sophus Lee and Felix Klein. They're wonderful. Do not read Paul Gordon. He's a nice guy, but ugly writer, not a good writer. But read them in the 19th century. Read 1920s algebraic geometry or differential geometry. They're beautiful, but they're hard. They're incomprehensible to people. They don't give clear foundations. They don't give clear definitions. They're starting to. That's what I said about everybody becoming a logician in Klein's sense. But in algebraic and differential geometry, even by the 20s, lots of people were not giving clear definitions. Stuff is, even if you already know the material, you can't read a 1920s description of it. Those fields. And you can see how far set theory, Bourbaki, category theory have clarified math. Now, mathematicians love to complain about these things. That Bourbaki, it's all theorem proof. It's too rigid. That's not what math is really like. I don't like to read it. I don't want to hear set theory. I don't want to hear any category theory. That's silly. It's just silly. These are all beautiful things, in fact. And they make math way easier to learn. In fact, they make math easier to learn. That's why they exist. Bourbaki could have published their books even if they didn't help, but you would never have heard of them. Nobody would ever have bought them. They became so hugely influential because they made it easier to teach math. Especially after World War II, there's a huge increase in university education. All of a sudden, it's not good enough to say, oh, in the math department, we take a couple of genius students and they go off and they figure it out for themselves. No, they got to be able to teach courses to good students. And they can do it using these things. These things made that possible. As Hal Brown would say, in my student days, mathematics depended on a special genius. Now, professors give lectures that good students can understand. And that's because of things like this. Well, she was talking about earlier. So there are prima facie two kinds of incompleteness. The Gödel phenomenon is inevitable in comprehensive foundations. You cannot avoid Gödel incompleteness if you give a foundation that could possibly cover all of math, even if it's quite fragmented, even if it's quite bizarrely lame, you're not going to get away with it if it's comprehensive. Because Tarski's elementary geometry, elementary algebra, they can't even define whole numbers. They're great. They're great for what they do, but what they do does not include defining whole numbers. You're not going to give a comprehensive foundation that does not meet Gödel incompleteness. Gödel incompleteness is generally remote from practical questions. And normally, they're fairly artificial things that you can prove are independent. Now, that's not to say that only artificial things are independent, and there's progress on trying to change that. But Gödel's own this, you know, Gödel comes along. He's a logic student. He looks at Principia Mathematica. Russell and White had written this 3-volume work using pure logic to prove that 1 + 1 = 2. That's actually the last theorem in the 3-volume work. And they say, well, we know you already knew 1 + 1 = 2, but you didn't know a rigorous way to prove it. That's what we're showing you, is rigorous ways to give proofs. Once you know how to prove 1 + 1 = 2, you'll find it lots easier to prove, say, the commutative law. That's all be easy. Once you can prove something, we're going to show you how to prove something. And then people say, well, Mr. Russell, is that all we need to know about arithmetic? Have your axioms left anything out? And this is a real question at the time. Is there anything in arithmetic that these axioms can't prove? And Russell says, well, nothing I've thought of, because I wouldn't have published them if I could think of things they left out. How do you know there isn't something? Well, I don't know there isn't something. I just can't think of it. And then Gödel comes along and says, ooh, I came up with something that you can't prove, that you can state in the language and you can't prove from those axioms. That's a little bit of a stretch with BM, because BM they have axioms, but covers that. So Gödel's the Gödel sentence that's not provable or refutable in PM is very artificial. But it's designed to work, and it does work. And in general, the Gödel phenomenon will be remote from practical questions in general. Concrete incompleteness, like the axiom of choice, is independent of Zermelo-Fraenkel. Some Goodstein theorem is independent of PA. You know about these things than I do, but there are concrete incompletenesses that can be very important to practice. For a lot of the 20th century, there were a lot of mathematicians who said, I don't care about the axiom of choice. That's a technicality. Actually, you do care about the axiom of choice. Analysis is quite different without the axiom of choice. You actually don't want to do analysis without the axiom of choice. And this is Borel, one of the French mathematicians who created modern analysis. He reads Zermelo on the axiom of choice, and he says, this is phony stuff. No mathematician would ever talk about this. This is not natural stuff. And Zermelo goes through a bunch of Borel's articles and quotes a bunch of them using, in fact, the axiom of choice without even being aware of it. He doesn't even know he's using it. And the amazing thing, because this does not happen often in philosophy or logic, Borel reads Zermelo and says, that's true. You're right. I did use this axiom. I used it because it seemed perfectly natural to me. Now, some other uses of it seem unnatural to me, but you're right. I said things that amount to the axiom of choice seem perfectly natural to me. We don't like to say that in foundations now. We like to say the other person's completely wrong every way, but so these are prima facie. That is, at first glance, these are different things. Okay. Is this inevitable? Is this in some way inevitable? It's a research project and one that you're pursuing. What is real here and what is historical axiom? It's a very legitimate open question. Is there really a hard distinction? If there is a hard distinction, exactly what is it? How do you recognize it? Is this a true dichotomy? It's a serious question. But crucially, Gödel's theorem is not particularly about Peano arithmetic. Lots of textbooks prove it for Peano arithmetic. That's the one I teach from. I prove it for Peano arithmetic. I think that's the right place to prove it. That's why I use a textbook that proves it. But it applies to lots of other axiomatic arithmetics. Robinson's Q's is very weak arithmetic. Raphael Robinson was a student of Alfred Tarski. Alfred Tarski, that had to be nice studying with Alfred Tarski, because a lot of his students did great work. Raphael, and that second B. I know a lot of English is really not pronounceable, just different sounds. But we don't have that. We're not that. That's just a typographical error. And Robinson said, well, what assumptions is this really using? And Tarski says, good question, go find out. Imagine Alfred Tarski saying to you, good question, go find out. And so Robinson says, oh, wow, I got rid of nearly all of panel arithmetic. I hardly need any of it to prove Gödel's theorem. It was really exciting discovery. And it's true. It's a finitely axiomatized theory. Gödel incompleteness does not depend on there being an infinite axiom set. It's already, Robinson's finite axiom set is already essentially incomplete. All of its recursive consistent extensions are incomplete. Exponential function arithmetic, sometimes called elementary function arithmetic, it's nice because it has the same initials either way. Is something that it's very interesting to me. Harvey Friedman boosted its importance. Second order arithmetic, the category of sets, Zermelo-Frenkel, Gödel's theorem applies unchanged to all of these. It's a really fantastically stable result. It's not sensitive to changes that a lot of logicians are very sensitive to. They're too sensitive, but Gödel's theorem is not. It just rides right across. Between the Gödel phenomenon and concrete incompleteness, Gödel's incompleteness theorem for PA is consequence there. We say PA can state but not prove that there exists a function phi such that every statement, every theorem stated in fewer than n letters has at least one proof using less than phi of n letters. If something is a theorem, it has a shortest proof. And there's a function that takes every sentence to 0 if it's not a theorem, and the length of its shortest proof if it is a theorem. You can describe that function in PA, but you cannot prove it's a function. You can't prove it's a well-defined function. If you could, that would circumvent the incompleteness. So it's not definable, it's not recursive. Now, from a set theorist point of view, that function exists. Indeed, there is a function taking every theorem to the length of its shortest proof. But that's set theory, that's not in PA. In PA, describe such a function, but you can't prove it exists. Harris-Harrington incompleteness for PA, he should be giving this. But okay, but I've got it so level. PA can state but cannot prove there is a function such that the smallest set which solves a certain coloring problem for these data NKM has size the function applied to NKM. You got a set of so many elements, you want to color the lines between them in such and so way. Oh yeah, you want to show that from this size up they can all be done. You can show that if it can be done for all sets of this size, it can be done for all larger ones. What's that size? Define this function, but it's not a recursive function, and it's not definable. It's describable in PA, but you can't prove that that description defines a function. Ramsey incompleteness. Well, there's more of these. The tetration function, wow. Y written above and in front of 2 is a stack of exponential 2's of length y. You write 2 to the 2 to the 2 to the 2. Well, but you write it down. This is a very fast growing function of y. Elementary function arithmetic cannot prove it exists. You can define it there, but you can't prove it exists. So that's a concrete incompleteness of elementary function arithmetic. Elementary function arithmetic can prove there's an x to the 2 function, but it can't prove that there's this variably iterated exponential function. That you can't do. That's a step up the hierarchy. So now that we know that there's no one foundation for all proofs, the different proofs depend on different axioms, what about ordinary number theory? What are there sufficient axioms for ordinary number theory as opposed to like these Gödel sentences? We know the PA altogether is not suitable for the Gödel sentence. But what about ordinary finite number theory? Hilbert in 1926 Consider the nature and methods of ordinary finite number theory. It can certainly be built through number construction by means of contextual intuitive considerations. Ordinary number theory is finite enough that we can understand all of it, not formally, we can understand all of it concretely. It's all like that. We can understand it. A concrete theory of arithmetic in Hilbert's sense. Hilbert says, okay, consider this statement. Every number n is less than some prime. This is actually how Euclid states what we call the infinity prime. It says there are arbitrarily large integers. There are primes. There are infinitely many primes. There are arbitrarily large primes. Take any number n, there's some prime bigger than it. He says this is not a concrete statement of arithmetic because it didn't tell you how far out you may have to look. If I say I want a prime bigger than 4 trillion, you don't know where that is. You can prove you won't have to look forever, but you don't know how far you'll have to look. So you don't really know what you're talking about when you say there's some prime greater than 4 trillion. Plus, you make it complete like this. There is some prime greater than 4 trillion and less than 2 to the power 4 trillion squared plus 2. Now I've told you how far you have to look. You don't have to look past 4 trillion squared plus 2. Now, you're not going to look there. You will, in fact, meet prime way before that. We can prove by harder theorems that there's some prime at most less than double that. But Hilbert says this is a concrete statement because this told you how far you have to look. There's a y that you will get to before this bound, which is greater than x in this part. Now we've made a concrete statement because we know how far we have to look. And he particularly likes when the bound can be given as an exponential function of an exponential of 2. It can be given with anything. So that's a concrete statement for Hilbert. Elementary function theory uses plus times an exponential in the bounds. Those are what you're allowed to put in bounds. You're not allowed to put that tetration function in. That would be a different thing. That would actually prove consistency of this theory. So it has to be stronger things. So he's saying number theory, unlike counter set theory, contains no infinity. Ordinary number theory always admits bounds. It's not just that everything is finite in principle. You can always say how big the thing you might have to look for is. So now you always know what you're doing in ordinary number theory, he tells us. This is not a mistake. It's vague. It's not, he hasn't really said exactly what he means by it. And it was controversial at the time. Godfrey Hardy, very, very famous English mathematician. He was a great cricket player. You know cricket? It's like baseball, but terrible to watch. Okay, they think baseball's terrible. Hardy was a very elegant man. He was a great mathematician at Cambridge. He's speaking of the prime number theorem. The prime number theorem gives an estimate of how many primes there are below any given number. And it's a very nice estimate. I won't go into details, but it's a nice estimate of how many primes. You give it an input n, it tells you how many primes there are less than that function. He says, no elementary proof is known of the prime number theorem. A proof of such a theorem not fundamentally dependent on the theory of functions of a complex variable seems to me extraordinarily unlikely. You're not going to be able to prove this without using the calculus of a complex theorem. We have certain views about the logic of the theory. We think that some theorems, we say, lie deep and others nearer to the surface. Hardy was a very appropriate fellow. Hardy was a prestigious fellow. Hardy was a fellow of his college. You're not going to prove this without the prime number theorem, without using complex analysis. If anyone produces an elementary proof of the prime number theorem, that is one that doesn't use complex analysis, he will show that these views are wrong and that it is time for the books to be cast aside and for the theory to be rewritten. And that's pretty much what happened. He's right about this. because there was an elementary proof and the older books were put aside and they did have to be rewritten because it really did change the nature of the field. The elementary proof is not easier than the analytic proof for students to learn, but it involves quite different methods. It really did change the field. This leads to what I call the wide open problem of Fermat's last theorem. How much arithmetic is needed to prove Fermat's last theorem? Okay, Wiles's proof for Fermat's last theorem is a wonderful achievement, and one of the wonderful things about it, one is how collaborative it is. There's a long series of proofs by various people pursuing this goal, and he puts a final cap on it. Another is how conceptual it is. And those two go together because you can't have a large collaborative effort if there's not a concept that people can learn, can get behind. It wasn't found by luck. It was found by pursuing a conceptual line. Does it use second order arithmetic? Does it use elementary function arithmetic? I'm inclined to think probably elementary function arithmetic. Now, any proof anybody gave of Fermat's last theorem was going to be a big deal. A lot of mathematicians have argued that Fermat's last theorem itself is not important. Very many have argued that. They've said, oh, it's just a side point. It's just a trick. It doesn't really relate to anything. And they're wrong. And the very fact that so many people said it shows they're wrong. Fermat's last theorem has long been a landmark. Anybody who told you in 1870, I don't care much for Fermat's last theorem, you could safely say, well, I'm not going to prove it either, but it's still a great thing. If it had been proved by a 5-page elementary calculation, that would have been a big deal, and it still would be a big deal. And we don't know it won't happen. Please do not go try to find a 5-page proof for Fermat's last theorem. Please, you will be wasting your time. You're not going to find it. But we can't prove you won't find it. We can't prove that some high school student won't announce one tomorrow and be right. We don't know that. Really bad bet. Really bad bet. We didn't know that. If it had been proved by a thorny, complicated argument like the Poincare conjecture, which took years to get refereed, that would have been a big deal. If it had been proved by a sprawling, disorderly mass like the classification of finite simple groups, that, however it was proved, would have been a big deal. And even now, any proof very different from the ones we have would be a big deal. The proof has been improved. Wiles's proof has been improved, it's been generalized, it's been streamlined, but not in a way that changes the fundamental character. Okay, Mark Kissin made a few improvements that got him a job at Harvard, but they didn't change the fundamental character of the proof. Like the Poincare conjecture and unlike the classification of finite simple groups, the current proofs of Fermat's last theorem have a clear motivating thread. This is not a technicality. Many of the arguments are technical in detail, but there is a clear conceptual thread, which I really feel has not been well presented by popularizers. I've tried to present it in this Springer Encyclopedia of Mathematical Practice. Not just doing it off the top of my head. I use Barry Mazur. I use a bunch of exposition. Now, the experts all emphasize the arithmetic character of Wiles's proof. They all say this proof is arithmetic. This is not some weird stuff. As one says, nobody who understands such proofs does anything but think about very small structures from the start till the end. I got this in an anonymous referee's report. I think I did reference reports, but they're anonymous. So and I agree. I know that every step can be checked in any given case. This is something I love to say. You take the proof, every step, we know how to check it in any given case by just naive arithmetic. There's nothing hard going on here. But in fact, the theorem itself, every case of the theorem itself can be checked, right? That's not news. You can check this. You can see that this is false. Now, you already know it's false because you know the theorem's been proved. This has to be wrong. But you can prove it's concretely wrong by a simple calculation. take the remainder on division by 3. I forget which. Anyway, the remainders on division by 3 are wrong. How do you calculate 3 to the 251st power? That's kind of a bit long, but to know the remainder on division by 3 is easy, because you can cancel that. So every case in the theorem, you can tell which are true and which are false, but that doesn't prove the theorem. Checking individual cases doesn't prove the theorem. And checking individual cases of steps in the proof doesn't prove those steps. Doesn't show it's provable in PA. If you knew that you could check all the steps, I guess that would show it's provable in Zermelo-Frankel, but it won't show it's provable in PA. PA is not complete with that kind of sentence. Compare the prime number theorem and other classical analytic number theory. I mean, you could check individual cases, but Hardy did not believe the prime number theorem could be proved in PA. He was mistaken, but he very seriously did not believe it could. And he said, if you show it can be, we're going to have to throw out all the books. He did show it can be, and they did throw out. Rather, what seems to be the case is not only did the experts know they could check every step in every case, they know how hard it would be to check every step. They can put bounds on how far you would have to look. Remember, like Hilbert putting a bound on how far you have to look for the next prime. They actually know, I think, my feeling is that they actually know how to put bounds, but it's hard to get them to say it. But yeah, still, I think there's a lot said here about it. Here's the proof. I'm going to outline the way the proof goes. If you had a Fermat triple, for some prime exponent p, a to the p plus b to the p plus c to the p, then you would get a cubic polynomial, x times x minus a to the p times x plus b to the p. That's a cubic polynomial in x, and it defines an elliptic curve. You can define that curve. Remember when I had that cubic curve that Poincare was drawing lines on? This is like that. This is exactly like that. This is descended from Poincare's idea. And more explicitly, you get a modular curve isomorphic to that cubic curve, where n is the product of the primes in A, B, and C. What is a modular curve? I am not going to tell you what is a modular curve. I will admit that I can't. I don't. It's not a super hard definition, but it doesn't speak to it, so I don't. And what's called a dominant map from that curve to this curve. We can get a kind of complex analytic curve that we know can map onto that elliptic curve. And we can get related elliptic curves with a lower n down to 2, which is impossible. We can show this can't happen by considering these maps from modular curves. Again, you don't know exactly what it means. I don't know exactly what that means, but I want you to know that experts, ordinary graduate students who are studying this know what everything here means, and they don't know the Wiles proof. Ordinary grad students have not mastered the Wiles proof, but they've mastered this part of it. So we by concrete calculations, we show that's impossible. Not do that. Now, just knowing that this doesn't happen for any kind, even if you did know that this is true for all concrete numbers, A, B, C, and N, that won't show it's provable in PA, because the Gödel sentence is already true for every concrete number, and it's not provable in PA. You know that, or in CFC. PA doesn't cover all concrete numerical truth, nor does CFC. Gödel shows us this. Is Fermat's last theorem provable in Zermelo-Frankel? People argued about this for a while. The Wiles proof refers to books that go beyond Zermelo-Frankel set theory because they use Grothendieck universals. Wiles doesn't use Grothendieck universals. Wiles never talks about that, but he does refer to books that talk about it. Currently, Kevin Buzzard has a very large grant to try to give the proof of Fermat's last theorem in Lean, which is a computer language. It's a computer proof of system. He has this summer a grant trying to transpose at least part of the Wiles proof into Lean. Lean uses Grothendieck universes. It uses any finite number of Grothendieck universes. Now, whether his proof will use them or not, that's another question. But the language makes them available. So they say, well, is it provable in CFC? Yeah, that actually has been done. People have seen very well how to get rid of the Grothendieck universes, prove it in CFC. Not a question. Of course, it's provable. Is it provable in finite order arithmetic? We have natural numbers and sets of naturals and sets of naturals, and this up to any finite level. Can you prove it there? Yes, you can prove it there. I showed that. Not by showing it, I prove a general result that all of the Grothendieck results that are referred to in any book we use can be proved in finite order. We know that because it has been done. But this uses arbitrarily high order, just always finite order. That's been done. I am sure it can be done in pound order. But I would really like to see a proof that it can be done in pound order. Not just believe it can be done. I would really like to see that proof. We give proofs like that. Angus MacIntyre, for example, has given proofs that various theorems can be proved in PA. There are proofs like that for other theorems. I would like to see a proof like that for this theorem. We don't have it yet. People get angry about this. Pound arithmetic is a natural pivotal theoretical reference. It's really an important landmark in theory strength. Pound arithmetic, it's a reference level. Everyone interested in mathematical logic should grasp this reference level. It provably cannot be the weakest arithmetic adequate to FLT because it's not the weakest arithmetic relative adequate to any of its theorems. Any theorem, if you could prove it in PA, that proof was a finite list of steps. You only used finitely many axioms. PA proves consistency of every finite list of axioms. It just doesn't prove consistency of the whole list. So we know if it can be proved in PA, it can be proved in some much weaker theory because every theorem of PA can be proved in a much weaker. That's just the compactness theorem, what's called reflexivity. It's not informative. It's informative about PA. I'm not sure. I argue that pound arithmetic cannot explain the expert feeling that the proofs are concretely arithmetic. Experts will all say, I just feel it. I feel that it could be done in arithmetic. One said to me, I'm not sure what pound arithmetic is, but I'm sure it can be proved in there. Well, you don't know what it is. Don't say that. Lots of people don't know what pound arithmetic is, but if you don't know what it is, please do not have strong opinions about what can be done in it. You don't happen to know what it is. But they have the PA is not concrete finite sense, exactly in Hilbert's sense. I think Hilbert's sense is relevant. Pound arithmetic allows you to make statements where you can't put any bound on how far out you might path. Pound arithmetic can prove statements like that. And I think that's what's not happening here. I think these experts are saying, when I was watching Wiles prove this stuff, I could see you wouldn't have to go more than so far out to cover that. I mean, I think, but PA doesn't care. Exponential function arithmetic cares. Because again, for Hilbert, to say that every number n is less than some prime is not a finite plane. To say that every number n is less than some prime that's less than 2 to the x squared plus 2, that's concrete because now you know how far you have to look. Is there a prime number greater than 47? Not only is there some prime number greater than 47, there's some prime number less than 2 to the square of 47 plus 2. You can put a bound. That's a ridiculous bound for that case because 51 isn't. No, not 51. I don't know. I think the experts, they're seeing bounds like this, that they aren't making a very big. They don't just feel like these calculations should end. They see how to bound the calculation. They see that should end fairly fast. They see it in their mind, at least vaguely, how it's going to end. I think. I don't think they're making up these things they say. I think this explains them. And that they can be uniformly verified. The proofs do use what's called cohomology. Cohomology is an algebraic tool for organizing calculations with groups, and it's such a good tool for organizing calculations with groups that for many problems in mathematics, notably including Fermat's last theorem, you try to organize all of your data and all of your constructions as groups so that you can use their cohomology. This is just normal. What is a universe? Grothendieck, when he was organizing cohomology, he said, fairly often we want to look at really large constructions that sort of go on forever. And one thing I might be able to do is show you they don't go on forever, but I got a better idea. Let's posit these universes that are so big that even if it goes on forever, it stays inside that universe. Just to save trouble, just to save trouble. To save trouble, I'm going to posit sets so big that Zermelo-Frankel can't prove they exist. But that means any progression you can define in Zermelo-Frankel, maybe it's an unbounded progression, it goes on forever in ZF, it stays inside some universe. I'm just going to do this to save worrying about how far any progression goes. And you can do that. But it was, in fact, it's progression. So Grothendieck universe has a plain explicit meaning. It's a universe in the context of type theories has a similar meaning. These are just things that are so big that you don't have to worry that any of your calculations will go outside of them. Now, probably for the calculations you're actually doing, you could put much smaller bounds. But maybe you don't want to do that on your first try. You don't want to worry about bounding it on your first try. So you use a universe. Replacement, Grothendieck's perspective. Angus McIntyre has said, okay, the proof of Fermat's last theorem, I gave you that outline. A lot of people did that. A lot of people did that. In fact, let's look back at that outline. A bunch of mathematicians said that you could prove Fermat's last theorem this way. A man named Eleglar, back in the 1970s, pointed out this. That would be an interesting qubit. If that could explain certain things, then Fermat's last theorem would be false. Okay, now that's not the direction we would have liked because we kind of thought Fermat's last theorem was true. So we think that qubit curve can't do those things. But even if it can't do them, that does, so how will we find a curve that does do them? We don't know. We don't know. So then Serre works with Rivet. Serre and Rivet show that if you have a modular curve, you can't have this happen. So the question was, that qubit curve, does it have to be modular? That was sometimes called the Taniyama-Shimura-Bay conjecture that all qubit curves are modular. All non-singular qubit curves are modular. And this becomes later called the modularity thesis because there was so much arguing about who did what in Taniyama-Shimura-Bay conjecture. So Rivet showed that it can't be a modular curve. So then the question was, how do you know that every qubit curve is modular? And honestly, nobody thought that was within reach. People thought that's too hard. We know it would work to complete the proof, but we don't believe anybody can do it. And Andrew Wiles is trying to do it. Andrew Wiles is a math professor at Princeton, tenured math professor. He does not want anyone to know he's working on this, partly because he doesn't want anyone to steal the idea, but more because he thinks people will laugh at him if they think he's working on it, because nobody believes it can be done. Does it? He doesn't. He proves that every cubic curve is modular. That's called the modularity thesis. That's the proof. That's the hardest step. That's the step Wiles did last that completed the theorem. Modularity thesis, and we call that MT. So McIntyre says, putting proofs of the modularity thesis into panel arithmetic will involve finding finite approximations of modularity and all the other principles that go into its proofs. McIntyre claims that he can convince all except professional skeptics that modularity thesis is really pi 0, 1, but the Gödel sentence is also pi 0, 1. So that by itself doesn't show anything. I mean, it's encouraging towards showing it could be proved in PA. But the Gödel sentence is famously a pi 0, 1 sentence and is not provable, the Gödel sentence of PA. So this is rather a red herring. Also, what I have argued is that normally in mathematics, when we're proving something, we don't just try to convince all except professional skeptics. Try to give a proof. You give a proof. And I would like to see a proof. First of all, we don't currently have a proof that the thesis is pi 0, 1. And even if we did have that proof, that would not prove that it's provable in PA. I would like to see a proof that it actually is provable in PA. The thing is, we haven't found the relevant finite approximations. Finding finite approximations to number theoretic results is a standard part of number theory. It's not some weird goal that logicians have. Number theorists constantly prove things by finding finite approximations, which means it can be hard to do. Finding finite approximations can be a very substantial new result. I don't know if finite approximations to the modularity thesis would be substantial results or not. It's impossible to know right now because nobody knows any of them. We don't have them. And the other principles that go into the proof. It would be great to see those finite approximations. It's conceivable that they would substantially improve our understanding of the proofs, that they would be hard, serious results. It's conceivable that they would be fussy and not enlightening. It's conceivable that they would turn out to be trivial if you just thought of something. We don't know right now. We know nothing about such things. Okay, that's the other point about if we could give those finite approximations, that's like giving bounds. If McIntyre has said that he has no idea whether this can be proved in exponential function arithmetic. Well, of course he has no idea whether it can be proved there because he doesn't know how it can be proved in PA either. If you don't even know how to prove it in PA, you obviously don't know whether it can be done in EFA. Very likely, if we had a proof that it can be done in PA, that proof would show us how to do it in EFA. Maybe trivially, maybe by hard results, don't know. It's certainly the only way you're going to tell whether it's provable in EFA is by seeing how it's proved in PA. Harvey Friedman has conjectured that every result proved in the annals of mathematics that can be stated in arithmetic is provable in EFA. It's his grand conjecture. Well, Fermat's last theorem is statable in arithmetic. It's a statement of arithmetic. And it was published in the annals. So great. If we can prove it's provable in EFA, that's great. We showed it's provable. If we can prove it's not, you've proved Harvey Friedman was wrong about something. Who wouldn't like to prove Harvey Friedman? Yeah, I would just like to see this spelled out. I have done sums to spell it out. Kevin Buzzard his Kevin Buzzard's grant would not require any gaining any information about this in principle, but it probably will involve that. Probably the only way he's going to make any progress on that grant is by eliminating this question, to some extent at least. So that's what I would like to see. I would like to see, because once we know it can be proved in PA, then we can ask what fragment it can be proved in, and that answer is likely to be very illuminating. Knowing it can be proved in EFA, that would tell you a lot about the theorem. Probably it would simplify the proofs also, because it would show you places where you could simplify them. Not necessarily, that's not guaranteed. But so that's what I would like to see us settle this question, not just say we're sure of the answer, but say how to prove that answer. That's what I. So that's what I've got for this talk. Maybe we can take questions and talk further about it. Yeah, I mean, I've got a few more slides. Do you want to talk about the use of complex numbers in number theory, or? Yeah. Okay. What is elementary number theory? Um, when Hilbert talked about elementary number theory, when Hardy talked about it, he meant number theory that doesn't use complex numbers. In contrast to analytic number theory. Oh yes, this is the prime number theorem. What does the prime number theorem say? Pi of n is how many primes are there below n? So pi of 47, how many primes are there below 47? So that's a precisely defined function. Currently, we have no precise definition that would tell you how to calculate that. We have approximations to calculate. Well, of course, in a way, yeah, if you want to know what is pi of 4 trillion, you just count up the primes up to 4 trillion. But you don't really want to count the primes up to 4 trillion. What we don't have is a neat formula that tells exactly. But we've had since the 19th century a very neat formula that approximates that number, which is you just integrate from 2 up to n, the argument 1 over natural log of t. That's a very good approximation to how many prime numbers there are less than n. This is a fascinating fact. Now, that doesn't look like it uses complex numbers, except that to calculate that integral, you don't want to try to calculate that integral by staying on the real line. You want to embed that function into the complex plane and use complex integration to calculate that integral. So this is what Hardy meant by involving analysis. Hardy thought the only way you're going to prove this equation, this approximation property, is by looking at integrals over the complex plane. You're really going to have to do that to do this. Today, that has changed completely. The expectation has changed completely. And George Kreisel was one of the main people to do this. And Angus McIntyre is one of the people who's done the most to popularize Kreisel's ideas. McIntyre very justly points out, Kreisel showed us, when you look at that, if you're familiar with the log function, you see the Taylor series. You know this is a Taylor series calculation. And you should, what we now, you look at that, and since Kreisel, you look at that and you think, that looks like arithmetic. That looks like you don't really need analysis here. You really just look at the Taylor series. You got upper and lower bounds on the Taylor series. Because at any rate, pi of n is an integer, right? There's some whole number of primes below n. So once you know the Taylor series for that integral, and you know that the result has to be an integer, you can find the integer bounds on that Taylor series. So today, since Kreisel, we look at that and we think, that's arithmetic. That's arithmetic of whole numbers. It's a disguised form of the arithmetic of whole numbers. You can treat it as complex analysis if you want, and this is a very handy way to calculate with it. But really, it's a disguised form of the arithmetic of infinite series. You can calculate it by a Riemann's complex zeta function. You should calculate it that way. People who want to calculate it do calculate it that way. But we now know this really is arithmetic of whole numbers. This is not really second order arithmetic. This is first order arithmetic, to put it in technical terms. Now, there are other uses of complex numbers that are transparently elementary. When you're talking about quadratic reciprocity, we can write a squared plus b squared as a product of two complex numbers. But that's just if a and b are whole numbers, that's whole number arithmetic. There's nothing serious going on with complex numbers there. But since Selberg and Erdős and especially Kreisel, that these things are elementary. These things are arithmetic. So the truth, in terms of comparing this with Fermat's last theorem doesn't even seem to involve anything like that integral. No, it's all algebra. It's all normally algebra of finite groups. So it really does look like arithmetic. It looks much more like arithmetic than that does. And nowadays, we know that's really arithmetic. It's not really even second order arithmetic, as long as you're talking about approximations. Now, if you want the exact value of that integral, now you're doing deep analysis. But since you know that pi n has to be an integer, all you need is to approximate that to some bound less than 1/2. Once you know an integer to within plus or minus 1/4, you know the integer exactly, because there's only one integer in that range. So this is really arithmetic. So Hardy was completely wrong in his belief that this stuff could not be arithmetic. He was very confident. He was extremely prestigious, skilled mathematician, did great stuff, and he was completely wrong in his estimate of what's elementary and what's not. Because this is absolutely elementary. Today, we just see how to make that elementary right away. Hardy never thought this wasn't elementary. Hardy never thought this really had to use complex numbers. But he did think that did, and he was just wrong. Riemann zeta function, some of what we know about the Riemann zeta function genuinely uses complex analysis, but most of it is just estimates, and it's really just arithmetic. And you can see that it's just arithmetic. But this is kind of a sidetrack on Fermat's last theorem, because the proof of Fermat's last theorem doesn't use stuff like this at all. It uses much more algebraic stuff that you can much more easily think would be arithmetic. And I expect it is arithmetic. I rather expect it's elementary function arithmetic. How hard would that be to prove? I have no idea. Literally, it may be that you could prove that it's elementary function arithmetic by proving some estimate that would win you a Fields medal. I don't know. There might be some estimate there that it is true, but extremely hard to prove. I don't know. There might be no such thing at all. It might be that if somebody had the time to really dig through all that reasoning, which is massive, there would be no hard steps at all. But even when you're talking about digging through a mass of material where there's no hard steps, the way you normally get that done is by organizing it well. Organizing can be hard. And so it's possible to get those finite approximations of MT might turn out to just require careful attention to the problem, because this is a long problem and nobody has yet given it that attention. It might turn out to require brilliant number theory to give a usable approximation. I mean, I can give terrible approximations right now, right? Approximation of plus or minus 10, but that's just because that's a terrible approximation. And when McIntyre says the mathematical content of modularity is conveyed by pi01 sentences, I would like to see that's actually spelled out. What are those pi01 sentences that convey the mathematical content? Don't just assure me that there are some. let's, do they convey the mathematical content? Certainly they convey it in some new way. Is it an interesting new way? Well, probably some versions of them would be very interesting. It's virtually certain that good enough finite approximations of the modularity thesis would be very interesting. Maybe so interesting that logicians aren't going to find them. That's going to depend on the next Godfrey Hardy to find it. I don't know. Don't know. Precisely, we don't know. And so I think it's not a good idea to go around saying this isn't worth looking into. Now, I haven't looked very hard into it. Angus hasn't looked very hard into it. Anybody who wants to not look into it can. But I wish Angus would stop saying nobody should look into it. That I think is actually a bad attitude. Because there might be something very good to find here. And Kevin Buzzard, maybe he'll achieve his goal without illuminating this at all. But I kind of think that to achieve his goal, which he's got like a $500,000 grant to do, he's going to have to address this. He's going to have to look at finite approximations. Well, his grant, as I recall, is to use lean to verify some steps of the proof. Well, you see, that's pretty vague. Yeah. I could verify some step of the proof myself. Somewhere in the proof. Oh, right. Somewhere there are places in the proof where he points out that 3 is not equal to 5. I can cover that stuff. But whether Kevin is going to cover substantial steps that don't illuminate this, I don't know. It could. He might not. I still think it's McIntyre says, I have no idea what arithmetic bounds are feasible for proving the modularity thesis. Of course, he has no idea what the bounds are because he has no idea how to approximate it. Even if you're just used to calculus, you know that approximating is a lot like setting bounds. Giving an approximation is like setting upper and lower bounds. So he doesn't know how to give the approximations. He doesn't know whether it can be bounded. I think it would be worth exploring. And I kind of hope that Kevin Buzzard's research will explore this. It'll certainly be adjacent to this, whether it will shed light on this. We have to see the research get done. Now, we'll say there's a difference between McIntyre and Harvey Friedman on this. McIntyre has said he's so confident this can be proved in PA that he really advises people not to waste time doing it. Harvey Friedman would never say anything like that. Harvey Friedman, you will never hear Harvey Friedman say, I'm sure that can be proved, so don't prove it. He'll say, I'm sure it can be proved. It's probably easy. If it's easy, go do it because it'll be quick. And if it's not easy, go do it because it turned out not to be easy. Harvey's never going to say, don't prove that because I already believe it's true. He's going to say, I believe it's true, so you should be able to prove it. And I would like to see this proved. I would like to prove it myself, but I promise I will. I would have got a grant for that. I would have got a grant for that if I thought I could promise that. I think it's something people don't understand about arithmetic. They really don't understand how big numbers can get. And if you tell them that, they'll say, of course I know, numbers get infinitely big. Yeah, but do you really know what infinitely big means? I mean, do you understand the principle that any procedure for calculation that I give you, like factoring a prime number, is it hard to factor prime numbers? Well, it is if they have 200 digits. And it's impossible if they have 10,000 digits, unless it ends with a 2. Good, it's divisible by 2. But people don't realize how completely infeasible problems are, like prime factorization of arbitrarily large numbers. Now, the whole banking world understands that that's pretty infeasible because their systems depend on it being infeasible. If you can quickly factor 1,000-digit numbers, probably what you should do is try to convince someone at Citibank that you can do it and see if they won't pay you a lot of money to hush it up. Don't tell the National Security Administration. They will want to hush it up, but they might not do that by giving you money. No. We all know procedures for factoring large prime numbers, and we all know that you can't do it for arbitrarily large ones. But I think by and large, people do not appreciate how every calculation eventually becomes. But I think that the calculations in the proof of Fermat's last theorem, not only, well, they become infeasible in principle, but not unboundable. You can give an infeasible bound, right? As soon as you know that something done, that you can solve a problem for n in 2 to the 2 to the 2 to the n steps, so that may be more steps than you can take, but you know the bound on it. That's what I would like to see. I think all of these steps can be bounded. I suspect that the experts who tell me, I know it can be done in arithmetic, they do know it can be done in arithmetic. And that's because every step they've looked at, they could see a bound. But they haven't stated all those bounds. And I'm not saying they need to. And I think that's what McIntyre's missing here. Let's see those finite approximations, or at least let's see bounds on the finite approximations. And I think that you might be able to bound the whole thing. You might be able to show that Fermat's last theorem is a theorem of exponential function arithmetic in a way that doesn't enlighten anything. That can absolutely happen. On the other hand, it could be kind of enlightening on some steps when you give a proof that it can be done. That proof could be enlightening. And McIntyre has said, if you give me 30 graduate students who don't need to find jobs and 5 years to support them, I can get them to produce a proof of Fermat's last theorem in PA. I look at that and I think that is not an estimate anyone can reasonably make. Nobody can estimate what 30 graduate students could do with 5 years research time. It's just not a reasonable estimate. And what we don't know is that, like I say, we don't know that a smart high school student won't actually give a proof of Fermat's last theorem in 5 pages tomorrow. There's absolutely no principled objection to having that happen. I promise you it won't happen. But there is no principled reason that I promise it won't happen. We don't know it. Will there someday be a 5-page proof of Fermat's last theorem? Well, there's a 10-page proof of the prime number theorem that people like a lot. I don't know. And at one point that seemed like impossibly hard. So this is why I call it the continuing challenge of Poincare, Gödel, Hilbert. Actually using what they found out, there are wide open questions. Once we know that you can't just talk about a proof, you have to say proof from what axioms. Now it becomes interesting to know, well, what axioms do we need for PA? The current published proof actually uses Zermelo-Frankel plus some universes if you include the references as part of the proof. Of course, published proofs are not complete. Nobody publishes complete proofs in advanced mathematics today. There's a 700-page book. It came out of the Boston University seminar on proof of Fermat's last theorem. 700-page book that will not enable you to read Wiles's proof, but it will enable you to read the key references after which you could read Wiles's proof. This is a complicated proof. Will it get boiled down? It's already been boiled down, of course. Every proof gets boiled down. But we don't know how far this will get boiled down, and I think it's worth exploring what we currently know about it. I haven't made it my first priority either, right? I have not devoted all my time to finding these bounds. I've put some time into it and given some talks on it, but and I just really, I wish Angus would take more interest in filling in the parts he doesn't know. He tells us many parts he doesn't know. Angus produced a fantastic article about whether it's a theorem of PA in this Horizons of Mathematical Knowledge. It's in a volume dedicated to Gödel from a Vienna meeting that came out about 10 years ago now. Angus wrote a fantastic survey of various steps in the proof and why he thinks they can be done in PA. And in that survey, he says repeatedly, here we would need bounds which we don't have. Here it would be helpful to have some meta theorems, which we don't have. When you actually read that article, you see him say repeatedly that we don't actually know how to do this. That's not what people take away. They take away the first part where he says convince all except professional skeptics. But he says repeatedly we don't know how to do various steps. That's normal and it's not devastating. But it might be nicer if we did know how to take those steps. It would be nicer if we doesn't mean it's a promising research. It might be too hard to make any progress on. The progress might be disappointing when you make it. It does mean that I think it would be better if we knew. And like I say, the main reason I print this is convince all except professional skeptics. That's not how we prove things. We don't prove things by saying only a professional skeptic would doubt it. We prove things by giving proof, by giving the reasons. So that's what I would